All right, so I'm sure you're enjoying the wonderful snow here. You might have seen falling here the other day, and you know, maybe trying to stay warm a little bit. But like I mentioned in class before, since we're not meeting today on Monday, we are going to do 3.1 essentially through this video. 3.1 is not like a long section; it's a very important section though. We go over pretty much all the shortcut ways to do the problems instead of doing the crazy limit question that we've been doing in kind of 2.8. Now, I am going to reference questions back from 2.8 when we do some of these questions here in 3.1. It just depends on what it is. A couple of questions in 2.8 that we did together, there is a pattern to be found there, and we're going to kind of use that pattern to help us find out some of these different derivative rules. All right, so we're going to start from the basics. We're going to do derivative of constant, because this first one here. Then we have derivative of just x. Then we have sum of difference rule, multiplied by constant. And the big one here, this is the most important one, it will be power rule. Okay. And so those are the ones we're going to be focusing on here in the beginning, and then we'll go from there doing some different examples. Okay. Now, if I look at a derivative of a constant, okay, we had limits of a constant, okay, and what happened there for a limit was it was just equal to the same number. But that's not how it works for a derivative. Now, the best way to kind of do this problem, okay, would be to look at a graph. So we're going to do that first. So if I was to look at a graph here, don't need this. This is when I was messing with something earlier. If I was to graph a constant, wow, okay, I'm really bad at drawing the lines on here. Haven't done this in a while. So if I graph a constant, try to actually do this good, not terrible. We'll just pretend that's straight. Okay. So if I was to graph this line, the constant would be something like this. Doing this nice little galaxy color. All right, so this is the graph equals like y equals c. Now, if I was to take the slope of this line, the slope is equal to 0. Derivatives are slope, right? So if we go back to what we did before in like 2.8, right? So I take f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So the problem here is since we have a constant function, what's going to happen is this turns into a constant, right? So if I was to really use this, it would be pretty much equals the limit as h goes to 0 of this becomes c minus c over h. Well, that's the limit of h goes to 0 of 0 over h, which gives me 0. Okay, so we can look at it two ways. We have the limit definition of derivative. This is 2.8 logic. Okay, we get to this result. Or if we look at the line, it always has a slope of 0. So if I look at a tangent line, the slope has the same value. Okay, so when it comes to 1, if I take f of x prime is equal to d over dxc, my answer is always 0. So if I take a derivative of any constant, so if it's a number 1, 2, 5, 10, negative 6, whatever, my answer is always 0 for that derivative. This is one of the easier ones because, you know, if you just have a regular number, it's always going to be 0. Okay? The next one is what happens if I'm taking the derivative of d over dx of x. So what if I didn't have a constant and it was just x? Well, we can kind of do the same idea, okay? So if I do the same thing, let's look at it as a picture. Come on, I wanted this, okay? Come on. It doesn't like me trying to do it this way. I also use my mouse because apparently I can't use my stylus. All right, so if I look at a graph of x, right? So let's do a little basic graph here. Okay, that's terrible. Let's try it again. There we go. So let's say this is y equals x. Okay. Now, if I was to look at the slope of this line, the slope is always 1, right? So the constant, the slope is always 0. In this case, the slope is always 1. So if I take the derivative of x, no matter where I put, no matter what point I pick, if I look at the slope of that tangent line, is always equal to the slope of this line itself. So we get 1 as that. Now, if we wanted to do it the fancy way, where we did all the, limit definition, okay, f prime of x would be equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. This one's not too hard because this is just x. You have x plus h minus x all over h. X's cancel. So you get h over h. Guess what? That is equals 1. So whether you look at it a graph and how it's a constant slope, okay, or whether you use the limit definition derivative, both these things kind of do a similar result. Okay, constants always give you 0 as a derivative. X is always 1. Or what can happen is if I have, let's say, I'm taking the derivative of like 5x, well, it's 1, but the 5 is still here, so we get 5. It's pretty much 1 times 5, you get 5. So essentially, when I take a derivative of a number, it goes to 0. Take a derivative of x, the x just drops off. And then we have to worry about what happens with x squareds and x cubes, which we're going to get to here soon. But these are the two basic ones. Okay, constants give you 0. Regular x just gives you 1 or the coefficient. Okay, the best way to look at it is we get the coefficient of x when we do this derivative. Now, if we look back at the note packet real quick, and I'm going to zoom in here because I might as well. So we have derivative constant d over dx of c is 0. Then d over dx, or x prime, is equal to 1, or the coefficient. Then we have the sum and difference rules. Essentially, if I'm taking two functions, add them together, and I'm taking the derivative of that sum, I can essentially take the derivative of them separately. Okay, and same thing happens with constants. If I have a constant times the function, I can factor it out. Okay, so if I was going to show you that in writing real quick, it's going to look kind of like this. We do it here on the right side. So if I had f of x plus or minus g of x prime, okay, this is going to be f prime plus or minus g prime. This is only true when you're adding or subtracting two functions. This is not true if you're multiplying or dividing two functions. Okay, so just be very careful when using this property. This only works when you're adding or subtracting two functions. Okay, multiplication and division, it's not true. Now, the only thing that is true with multiplication is if I ask you to take a constant times a function prime, it's just the constant times the derivative of that function, which a good example is this here. Okay, this is what this is doing. The 5 is multiplying x. Well, 5 is a constant, but I know the derivative of x is 1, so that's what we get 5 times 1. The 5 is the constant being factored out. 1 is the derivative of just x multiplied together. Okay, again, this is a very popular rule. Now, what's going to happen is I'm not expecting you to necessarily write those steps every time. Like if you're dealing with like a polynomial and we're taking the derivative of it, we just assume we know to take the derivative of everything individually. Same thing with constants. We take the derivative and we just worry about that constant at the end. Okay, so these are two rules that are used a lot, but you're not expected to like write out every detail with those steps. I mean, it's kind of sometimes inferred. And when we do a couple examples, you'll see. You'll see how it goes. Now, the one that's more interesting the one we've been waiting for, is number 5. Number 5 is a very popular one. It's called the power rule. This helps us with anything that's an x with a certain exponent. Okay, so if I look back at number 2, derivative of x is 1. But what happens if I have x to the second power, or third, or fourth, or fifth, or sixth? What are we going to do there? Well, to help us out that, let's go back and look at our questions we answered in 2.8. So if I go back to 2.8 real quick, all the way back here. When we did f prime, f of x equals x squared turned into 2x. Example 2, this x squared minus 5x plus 7 turned into 2x minus 5. Example 3 turned into 6x minus 2. Example 4 turned into 3x squared. So if I was to kind of write those down, right, x squared turned into 2x, x cubed equaled 3x squared. Let's see if we can figure out the pattern. So let's make some room. Go down here. All right. So if we had, I'm going to change the color back to black. F of x was x squared. Then f prime, so our derivative, was equal to 2x. When we had 3x squared, this turned into, when we took the derivative, 6x. When we took x cubed, it turned into 3x squared. So the question is, if I look at where we started and where we ended, is there a pattern for these cases? Now, for some of you, might be like obvious, and some of you guys might see it, but you're not sure exactly how it works. But essentially, if I look at the power, right, this used to be a 2 up top. Well, now that 2's in the front, and then we've decreased the power by 1. All right, it's the same pattern hold. We had a 2 on top. It multiplied the front, so it became a 6, and then became a power of 1. Here, 3 multiplied the front. 3 times 1 is 3. We minused it, so now it's 2 on top. And this is our pattern. So when we deal with anything that's an x to a power, okay, we essentially are taking the exponent, multiplying the front of it, okay? So I'm taking the exponent, multiplying the front, and reducing its power by 1 every time. That's the trick. So in general, if we're looking at in general, if f of x was equal to x to the power of n, then f prime is equal to the power multiplying the front, and then we minus the power by 1. This is power rule. It's one of the easier ones. At first, when you do it, it's kind of strange, but this is a one we're going to use like a lot. Okay, it's essentially the case you want to see most of the time. Okay, in the beginning, once you get comfortable using it, this is what you want to do for everything. You're wishing it's this, right? You're wishing it's a constant, you're wishing it's x, you're wishing it's a power rule. Okay, because those are your like main 3 easy ones. Now, of course, there's other options, okay, that we have to kind of, be aware of. And that's what chapter 3 is kind of all about. We start with like the beginning, and then we just add and add and add. And what's going to happen, just give you a warning, is there's going to be a lot of rules that we're going to keep track of. Okay, it's kind of like we're adding a bunch of tools to the toolbox. Okay, right now we have a couple things, but as we go further, there's going to be a lot of things you're going to have to remember. There's a lot of derivative rules. Okay, these are just the basics to start, but we go through a plethora of them. So just be prepared. It's best to try to prepare yourself now and kind of try to get yourself remembering them and get used to them in the beginning. So when you start adding the new ones, it's not like you're trying to remember the whole thing at one time. Okay, that's my recommendation. Now, we do have some examples we're going to try here, so let's take a look and see what we got. So if I go back to 3.1, okay, there are other notations we can see for a derivative, so I have a whole list here. You got f prime of x, y empire of x, dy over dx, df over dx. These are all interchangeable, okay? A lot of times you see f prime, pretty popular. Dy dx, also very popular. Okay, if the equation is written as y equals, that's when you see the y primes. Okay, you will see all these notations at various points of this course. Okay, so I wouldn't get super hyper focused in one or the other. I think that's actually kind of a mistake. So based off personal experience, when I did Calc 1 back in the, old years of 2012, we just focused on f prime the whole time, and it was really easy because we didn't have to worry about the d over dx thing. And honestly, I think it was probably not a great idea because when we had d over dx stuff show up, we just weren't comfortable with it. And so it made the questions harder than they really needed to be because we were wrestling with this extra notation. But these are all the same thing. So if you see d over dx, dy over dx, or a prime, just think derivative. Okay, so if you see those notation pieces, you have to think derivative. Okay. Now, example 1, we have a couple different ones here we're going to do. Okay, we hit example 2. We're doing the same thing, but we're just taking it one step further, and then we're going to add an extra tool to your toolbox before we hit the last example. Okay, so let's go ahead and take a look at these examples here. Part A is really simple. It's 4x to the 7th power minus x to the 5th. Now for all these parts, we're just asked to find a derivative. So we're asking to find d over dx or f prime or whatever you want to use as your notation technically. Okay, so let's go ahead and take a crack at it. So example 1. This is going to be part A. We have, I'm going to call it f of x, just because I feel like it. You don't have to do that. It's going to be 4x to the 7th minus x to the 5th. Now we're asked to find the derivative, so I'm asked to find f prime, or you're taking d over dx, this whole thing. Okay, I'll show you that notation too. Now, if I look at what I have here, I have two x's. One's power 7, one's power 5. This is going to be a power rule example. So the way I'm going to do it is the 7 multiplies with the 4. So I have 4 times 7, x to the 7 minus 1. I'm going to write out the whole thing. Then this becomes 5 in front of the x, and then I minus 1 to that power. So if I clean this up, 4 times 7 is going to be 28. And then x gets reduced to the 6th power, and this becomes 5x to the 4th. And you're done. That's it. If you had to do the limit definition derivative, you probably take the whole day to do it because you would have to literally raise everything to the 7th power, raise everything to the 5th power, and that's going to be interesting. Okay? Popular word, interesting. Be very interesting. And so that's not really recommended. This is way faster, saves you a lot of time, especially with complicated x's with more larger exponents. Okay, so this is going to be what we're going to use as that derivative. Okay, so we get 28 because 4 times 7. We minus 1, so we get 6. And then we minus 1 for this power is 4, but then the 5 multiplies the front. Okay, and this is what we're looking for. This would be our answer. Now, part B. If I do it the other option, as you hear my dog bark at probably people outside in the snow, you get pi x squared plus 117x minus e squared. Okay. Another notation you can use is the d over dx notation. Essentially, it's like almost like you're multiplying it. What's going to happen here is we do everything like normal. It's the same thing as saying f prime. There's really no difference between these two things. Okay. Now, if I was to take a look at this pi x squared, okay, the 2 multiplies the front. Pi is just a number. It's 3.14, yada, 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 right? So we're going to get 2 pi x, because we reduce it by 1, 117x, the x just drops off, so you get 117. And now the real question is, what happens with this thing? So, we're minusing e squared. E is another number like pi, okay? It's irrational. It's like 2.718, yada, yada, yada. Goes on forever. If I square an irrational number, okay, it's not like it's changing the way it's going to be. It's still going to be a number, right? So this is a constant being squared, okay? So what you can do is you can say that this whole thing here is just the same thing as like c squared, essentially. Now what that allows us to do is if it's a constant, it just turns into 0. E is tricky because there are some times where it doesn't turn to 0. Okay, you're going to see that rule at the end of the video here. But if you have just e squared or something like that, it's a constant, it just goes to 0. So really all I care about is 2 pi x plus 117. This will be the result we're looking for. So a and b are very similar. Okay, a is just a regular polynomial, pretty basic. B is still a regular polynomial with some weird parts to it that kind of throw you off, but it's essentially the same thing. There's real no difference between A versus B. Now, parts C and D are a little bit different. We have to kind of do a couple things here. And we're going to try to see how these work, because they are a little different. Not in a bad way, but there's just a little more stuff you kind of have to do in the beginning to get it to make it work. So if I look at part C first, make sure, yep, this one. We're given 3 times the square root of x minus 2 over x to the 5th. Now, this is a little weird because we don't really like the way this looks, but we can kind of change these to make it look more like parts A and B. So I'm going to suggest is before we do anything derivative related, I'm going to rewrite this as 3x to the 1/2 minus 2x to the negative 5th. Okay, so we get 3x to 1/2 minus 2x to the negative 5th. And we're going to take the derivative of this thing. The reason why I do this is because if I rewrite them, forgot, gotta use the good old mouse here. If I rewrite them, it looks more like this, right? And that's just power rule, just with weird numbers, right? We can do power rule with things that are rational, that's fine, or negative numbers, it still works. It's gonna look a little different because when I do this, the 1/2 times 3, so you get 3 halves. I should actually do this. Actually, let me yeah, I'm just gonna do this real quick first. I want to make sure I'm proper here. All right, so if I do the derivative of this thing, okay, I don't need the equals anymore. If I take the derivative of that, you're gonna get 3 halves x to the. Now, if I take 1/2 and a minus 1, we get a negative 1/2. So that's kind of the weird thing. Minus negative 5 times negative 2 is negative 10. And if I subtract 1 from negative 5, we get negative 6. Now, if I clean this up a little bit, all negative exponents go back into a denominator. But this one's negative and a root. So what happens, you get 3 over 2 times the square root of x, technically. This turns into a plus 10 over x to the 6th. And this will be the final answer. Now, I encourage you to try to simplify when it's something like this. There are going to be some examples in the future and problems we do in the future where we don't want you to simplify, but I think you can kind of go from here to here. I don't think that's that ridiculous to make you do. There's gonna be some problems though you'll do in the future where it's gonna be like, yeah, don't even bother. You don't even bother trying to do that. So here I think it's reasonable that we can assume for you to go from here to here. I think you can handle it. I will encourage you and would want you to try. Now, D, very similar. Then we have -5 over the square root of x plus 11x to the 2/3. How nice. They already have it in a rational form for us. Now here, same thing. If you have any pieces that don't have your typical x to a power, we should probably fix that. So in this case, it's going to be -5x to the 1/2, but now it's negative because it's on the bottom, plus 11x to the 2/3. That's already good for us. We're going to leave it alone. What's going to happen here is when I multiply this through, the -5 gets multiplied by -1/2, so that's 5/2. And we get x to the -3/2 if I subtract 1, plus 2/3 multiplies the 11, so it becomes 22/3. And then we get x to the 1/3, but negative. If I rewrite this, to kind of make it look like over here, we're going to get essentially 5 over 2 times the square root of x cubed plus 22 times 3 times the cube root of x. This would be like the formal, everything put together very nicely answer. Now I'm going to put d over dx technically here. So I rewrote that into this piece. I took the derivative of that, and this is the work as it goes down. So -1/2 times the -5, so 5/2, minus 1 makes it a bigger negative, -3/2, 2/3 times 11 is 22/3, minus 1, -1/3. When you put that in the bottom, it becomes a cube root of x, because now we're dividing by 3. This becomes a square root, and this number always becomes the power of x, using our rewriting rules. Again, this is a little more advanced, but I think you can handle converting this over. I would encourage you to try. It's good practice for you to do. Now, all 4 of these little examples here are just strictly doing a derivative. Okay, they all required power rule, right? One of them had derivative constant, one of them had derivative just x. Okay, so this is all those ones on that first page. Now, a question they can have you do is more than just find the derivative. They can ask you to find the derivative and then evaluate the derivative. So if you look at example 2, so go back real quick and take a gander. So example 2, they say, hey, can you find g prime of 1 if g is this? So we're tasked with trying to find the derivative of g, and then once we find it, we got to plug in 1. So my answer here is not just an equation. My answer is going to be like a number, okay? And that's something you kind of have to be mindful of when you're doing these. So let's go ahead and try it. So this is example 2. Where's my thing at? Come on. What's going on? There we go. All right, that was weird. Okay, so for example 2, we need to find g prime of 1. We know g of x is equal to, and I'm going to write it down, 4 times square root of x plus 3 times x, or 3 over x to the 4th, minus 6 times the cube root of x squared, and then plus the square root of 5. Let's double check to make sure I have that correct. Looks like it. Okay. Now, like the previous questions, I'm gonna not use this exactly. I'm going to change all the x's to things where it's got to be, so I can actually use power rule. So it's going to be 4 times x to the 1/2 plus 3 times x to the -4, and then it's going to be minus 6 times x to the 2/3. And I'm going to just leave the square root of 5 alone because that's just a number. So when I do g prime, 1/2 multiplies to 4, so we get 2x to the -1/2 plus 3 times -4, but that's just a -12, x to the -5th. Multiply this together. -6 times 2/3, get -4, x to the -1/3 now. And this becomes 0. Now here's the deal. Don't bother trying to rewrite this into this form. You don't have to. You could. It might make your life a little bit easier, but you could technically just plug in 1 into your calculator and do this and be fine. But if you just really want to be, fancy, let's say you did it anyways, you get 2 over the square root of x minus 12 over x to the 5th minus 4 over x to the cube root of x. 4 over the cube root of x. Now, conveniently, we're asking you to find g prime of 1. So this is not the final answer, okay? We want to find g prime of 1. So that's just going to be 2 over the square root of 1 minus 12 over 1 to the 5th minus 4 over the cube root of 1. So all happens here is just get 2 minus 12 minus 4. Well, that's just going to be -14. And this will be the answer. Okay. Remember, we're trying to find g prime of 1. So g prime of 1 is -14. We have to find this first, right? We need to find g prime. If we don't know g prime, we don't know g prime of 1. So we have to go through the work of solving it and then plugging it in. If you're doing like 2.7, you would have to use your limit definition, plug 1 in for x, do all the modifications, yada, 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 and then get to here, right? Which is okay, but for a question like this, definitely don't want to do. So these derivative rules are going to save you a lot of time answering similar questions you had in the past, okay? It just depends on what we're looking for. So you want to, look over carefully, do each rule you need, but overall, this beats doing a limit indefinitely. Okay, doing a limit takes a lot more time than doing this. So that brings us to the last little bit. So e is a number. However, e squared, e to the third, e to the -2, all numbers. But if I change that number to an x, we now have a completely different question. Okay? If I have e to the x, like we see here, okay, the derivative of e to the x is itself, which is great. That's one of the easiest ones we have. However, this only works if it's e is the base of the exponent and the power is x. If it's e squared, it's 0. If it's just e, it's 0. If it's e to the x, it's e to the x as a derivative. Okay? However, you gotta just be careful, because what happens is, as soon as you do this rule a couple times, you just start making e this every time, no matter what the power is. Okay? You have to be careful of what it is, so you don't accidentally start putting extra things that shouldn't be there. So let's go ahead and try. Let's try the 2 examples here, so you can see how it works. So for example 3, we have part A, g of t equals -3 e to the t plus 3t times e minus the natural log of 5. Now, we want to find g prime of t. Now, don't be freaked out. They're just replacing x with t. It's not really changing the problem too much. So if I look here, e, number, but raised to a power, that's t. That's a variable. So my derivative is just the same thing. It doesn't change at all. The negative 3 stays in front. No change. Don't even do anything. Now, when I look here at this one, okay, we look here at this one, right? Where do we notice the e is? Okay, the e is the exponent with a power of t. This is power rule, although it's a very weird one. Okay, it's a funny one. So you're going to get plus 3e t to the e minus 1. E multiplies the front, we have to subtract 1, but since it's irrational, we can't really write this as a nice number. And then we have this minus natural log of 5. Well, you can just really type that in the calculator to get an answer. This is a number, so you get minus 0. So our final answer would just be negative 3e to the t plus 3e t to the e minus 1. This would be our final result. Yes, this does look a little weird, but I did it on purpose. I switched these two on purpose to challenge you and to make you think, what do we really do if they're not in the right places? Okay? So you always had to have e to a variable. E to the x, e to the t, e to the something that is a variable, not a number. If it's a variable, we just rewrite the equation, essentially. That's our answer for a derivative. But as soon as the exponent's a number, it's 0. And that brings us to part B. Now, this doesn't have an e's in it, but it's a little weird. We have f of x equals 2x cubed minus 4x plus 3 all over the square root of x. Now, if we look back at our rules, we had a rule for constant x adding or subtracting components, constants multiplying, power rule, and this E one. We didn't really have a rule that had division, at least not yet, and that's intentional because the division version is really complicated. But when you're left with things like this, we don't really have a nice way to answer this problem right off the bat, right? Because I don't have a rule that we know that allows us to take something on top, divided by something on the bottom, and take the derivative of that at the same time. So usually when you hit a question like this, what's easier to do is divide this through and hopefully things work out. Now in this case, it's good because if we look at the bottom, it's just this single thing here. It's only the square root of x. Okay? If this was more than that, we'll have a problem. But since it's a single term, it's a monomial, square root of x, we could divide this through, and that's what we should do. So I'm going to rewrite this as 2x cubed over the square root of x minus 4x over the square root of x plus 3 over square root of x. And the reason why I'm doing this is because I can rewrite all these individual things to be some x to a power. When we divide, they subtract, so it's 2x. Technically, this is 1/2 being minus the 3, so we're going to get 2.5. We're going to say 5 halves minus 4x to the 1/2. And now this one is funny because there's no x at all, so it just stays as a negative 1/2. And this is what we're taking the derivative of. If we start going from here, it's a lot more complicated. So if I do f prime, 5 halves times the 2 becomes 5. X to the 3 halves, so you subtract 1 from it. Minus 2x to the negative 1/2. Minus 3 halves. X to the negative 3 halves. And this is probably something you could probably just leave alone. I think this is okay. I mean, if you really wanted to rewrite it and be, kind of showing off a little bit, it's 5 times the square root of x cubed minus 2 over the square root of x minus 3 over 2 times the square root of x cubed. This would be like the formal way to put it. But honestly, this is okay. You don't have to necessarily do this every time. If they're basic ones, I would say go ahead, do it, because you can. But when you get like this kind of weird, I'm usually looking at this first anyways to see, do you even have this? And then I usually check this to make sure you didn't mess it up. But usually I'm okay with this, right? This is fine. So you don't necessarily have to simplify. But once like this, I mean, it's not terrible to do so. This one's a little bit more tough, right? But it's up to you. Okay, you don't always have to simplify everything, okay? Especially when you do quotient rule, which is the like we do the real division problem the hard way. Yeah, you're not simplifying those. That'd be not so fun. Okay? So, that's all 3.1. So what did we do? We talked about derivatives of a constant, x, a power rule, and e, and we also went over the minor details of, hey, you can distribute derivatives across addition and subtraction. Okay, that's how we did all these problems, by the way. Notice all these problems had addition and subtraction. And what did I do? I just did derivative of everything separately. Okay, I didn't even make a big deal about it. Okay, that's what that rule 3 is. And rule 4 is, hey, I could take the derivative of the x part and then multiply the constant. I did that for all these too. Okay, so when you're really looking at it, when we're doing these two rules, we do the rule 3 and 4, the sum of difference rule and constant multiple rule. We just do them all the time, and we don't really like make a big deal about it. Okay, we kind of just do it. Okay, the things that are the actual like tools in the toolbox, constants are 0, x's are 1, or just the constant in front. Power rule is always power multiplies the front, then reduce it by 1. And then the other tool is any derivative of e to the x or e to some power is itself. Okay? Very important. If it's just e or e to a number, it's 0. Okay? That's usually the tricky one. A lot of people like this one because you don't have to do much work. You just rewrite the number. But you can easily do too much or do too little. You just have to be very careful what you're looking at. Okay? All right, so when it comes to stuff to do, we do have the paper homework for this due like next week on Monday. So if you want to go ahead and take a look at that and start working on those derivatives, that's probably a good idea. You're going to have a few of them on that quiz on Monday next week too. You can take a look at the paper homework. And obviously we're supposed to have that quiz today, which we're not doing since we're not meeting. So what's going to work with that is hopefully tomorrow, Tuesday, we'll be able to meet up in person to do that. But if for some reason that's not in the cards, we'll just do it on Wednesday or something. Okay. And then we'll do another video like this pretty much on 3.2. And we'll kind of just keep the train moving forward, and we'll just do the quiz next time we meet. So it'll give you a little extra time, worst case scenario. Okay. Now, if you have any questions on any of these examples, or you need me to kind of reiterate something, or you're kind of confused on something, definitely email me. I'm around to help you. So if you need the assistance, please let me know. Like I mentioned before in class, when we meet back up in person, I'll spend some time answering any questions too, just in case there's something that comes up between now and then anyways as you're working on stuff, okay? All right, if you need anything, please let me know. Otherwise, I'll see you guys on Tuesday, hopefully, if worst case, Wednesday.